1 egg, 2 eggs, 3 eggs. It's important to have a sufficient breakfast. If we're trying to estimate a parameter, it's important to have a sufficient statistic. Today we're going to learn about a new theorem which allows us to show in an easier way that a statistic is sufficient. It's called the factorization theorem. And we can also use the factorization theorem to find a sufficient statistic. So far, we have shown that a statistic is sufficient by using this theorem, which says if we write the joint PDF or PMF of the random variables in the sample, and then we divide it by the PDF or PMF of the statistic, and the parameter cancels out, then we have a sufficient statistic. What color do I want? That one. Then we have a sufficient statistic. This approach requires that we find this density down here. So we have to first do some work to figure out what is the distribution of this t. This can be hard to find. Can be hard to find. So there's another approach which doesn't require us to find this, and it can be a lot simpler, and that is coming from this theorem, which we're going to call the factorization theorem. So it's a check for sufficiency by factorization. So the setup is the same. We have some random variables in our sample with some joint PDF, or it could be a PMF. Nothing changes between the discrete and continuous cases. And we have some statistic, a function of the data values, and we want to check for whether or not it's sufficient. This factorization method says if we can just take the joint PDF or PMF of the values in the random sample and write it in such a way that we get a function of the sufficient statistic and the parameter times a function of just the data values, which does not involve the parameter. So over here, this does not involve theta. Then we can just claim that t is a sufficient statistic. So let's see how this works in an example. So here we've got a random sample from the beta distribution. The first parameter, this alpha, is equal to 1, and this theta is like our beta. And we want to check whether this crazy looking thing is a sufficient statistic for theta. Now, if we were to try to do this in the way we've used so far, we would have to find the distribution of this. That is, we would have to find the PDF of this thing so that we could put it down here, and then we would have like our joint PDF of x1 through xn up here, and our PDF of ft down here, and we would ask, does theta go away? Okay, so we only have one parameter here, it's this theta that we don't know, and we want to see if this is sufficient for theta. So we would be asking, does theta go out of this ratio? But in order to even write down the ratio, we would have to find the PDF of this thing. And I, your professor, have no clue how to get the PDF of this thing. It's very complicated. So it's nice that we don't have to use that approach to check whether this is a sufficient statistic of for theta. We can use the factorization theorem, which is this one. So how does that theorem work? First, it begins with just writing down the joint PDF. We're in the continuous case, so it's a PDF of the random variables in the sample. I have x1 through xn as independent, so their joint PDF is going to be the product of their marginal PDFs. Okay, so remember the beta PDF, if I have alpha equal to 1 and beta equal to theta, it's going to be 1 plus theta, 1 theta. Give myself more room here, and then x raised to the 1 minus 1, 1 minus x raised to the theta minus 1. Okay, which this guy is going to go away. This is just equal to 1. So here I have, that's right, theta plus 1 over gamma of theta. And here's 1 minus x, theta minus 1. Okay, we can simplify that even further if we want to, since we have this property of the gamma function, which tells us this. Is that right? If I have, let's check it for an integer. I know that this is like n minus 1 factorial. And so if I do n plus 1, that is n factorial. But I can write n factorial as n times n minus 1 factorial. And n minus 1 factorial is gamma function of n. So yeah, I have this property of the gamma function that I can use. So this up here is just theta, like this. So I can write it as theta 1 minus x, theta minus 1. So we can write down the joint PDF as the product of these guys. So we have theta 1 minus xi, theta minus 1. And it might be useful to remind ourselves of the support of the beta distribution. I think it's especially useful when we're using the factorization theorem to include, whenever we write down the density, an indicator function which tells us the support. Okay, so I know that the beta distribution has support on the interval 0 to 1. So why don't I just go ahead and include here an indicator function to that effect. So here I'm going to have indicator function 0, x, 1. Okay, now here I'm going to have indicator 0, xi up to 1, since I'm just taking a product over those. Okay, now what in the world were we trying to do again by using this factorization theorem? It says t is a sufficient statistic if, when I write down the joint PDF, I can somehow write it as the product of two different things, one of which is a function of that statistic and the parameter, and the other of which doesn't involve the parameter, but just involves maybe the data values. So let's see if we can do that. If I apply this product, I get theta to the power n, okay, because it's going to look like this. It'll be theta times 1 minus x1 raised to the theta minus 1, indicator of x1 between 0 and 1, times theta times 1 minus x2, theta minus 1, times indicator that x2 is between 0 and 1, times, and it keeps going until we get all the way out to the nth one, indicator that the nth value is between 0 and 1. Simplifying this, I see that I get theta n times, so theta to the power n. And then I can write these guys all as 1 minus xi to the theta minus 1. And then I can write all of these indicator functions using another product like this. Let's go down to the next page. So I'm not quite there yet. I want to somehow get this to appear down in here. And it's almost there. I've got this thing, but each one of these is like raised to the power theta minus 1. I can write this like this. Okay, since each of these things in the product is raised to the power theta minus 1, I can raise the entire thing to theta minus 1. Because if I have like a raised to the b times c raised to the b, that's the same thing as a times c raised to the b. Okay, and so now I've got that product of indicator functions also out here. And here I am. Okay, let's look at this part and this part. Here is my sufficient statistic, or the statistic that I'm considering. So this is my statistic, and here is a function of my statistic involving the parameters. So this whole thing I'm going to call my function g, which is a function of my statistic and the parameter. And this over here I'm going to call my function h, which involves only the data and not the parameter anymore. Okay. Now, since I've identified a g and an h, where the g is a function of the sufficient statistic, or a function of the statistic and the parameter, and h is a function of only the data, and I can write the joint PDF of the random variables in the sample as the product of these two things, then I say by the factorization theorem, this guy, which is the product of 1 minus the xi's, is a sufficient statistic for theta. Okay, and I'm done. I have shown that it's sufficient. So if I had tried doing it the other way, I would have had to get the PDF of this thing. But that is too hard, so we don't do it. We can use this factorization theorem. Okay, let's do another example. I've got a random sample coming from a distribution with this PDF, given by this thing, and I want to check whether the sum of the xi's is a sufficient statistic for the parameter mu. Okay. So the first thing I need to do in order to use the factorization theorem is write down the joint PDF of all my random variables. Since these guys are independent and they all have the same distribution, their joint PDF is going to be the product of their marginal PDFs. So this thing x minus mu squared, squared to the minus 1. Okay. And I need to write xi minus mu. Okay, so when I take this product, I can get pi raised to the power n, and then I've got, or sorry, to the power minus n. Let's write it as 1 over pi to the power n. Okay, 1 over pi to the power n. Now I've got 1 plus xi minus mu squared to the minus 1. And I'm kind of stuck. So taking the product of this thing, there's no nice way to simplify it. So we cannot make anywhere the sum of the xi's appear. Okay, so I'm not going to be able to write this as a function of the sufficient statistic and of the parameter. So basically I can't make the sum of the xi's appear, and so I'm not going to be able to find such a factorization that is needed for the factorization theorem. So we say sum of the xi's is not a sufficient statistic for mu. Let's remind ourselves what that means. That means if I collect data from a population whose distribution has this probability density function, if I take my n data values and I compute the sum of the xi's, and then maybe I delete all these values, and so I just know what the sum is, then I've lost some information about mu. That's what it means that the sum is not a sufficient statistic. It means keeping only the sum and throwing away the individual values causes you to lose some information about mu. However, in the previous example where we did show sufficiency for this particular beta distribution, if I compute the product of 1 minus xi and store that number somewhere, then I can delete all the individual values, and I have lost no information about the parameter theta. Until now, we've considered statistics which are some function of x1 through xn, and we've considered a parameter which is only one value. We can have parameters which consist of several different values, say theta 1 through theta d, all wrapped into theta, and we can have statistics also which consist of multiple functions of the data, so say k functions. So we could take our x1 through xn, and we compute one function, say t1, then we compute another function t2 of the data, and some up to the function tk of the data. Okay, and then we might be interested in showing whether that collection of statistics is sufficient for this collection of parameters. We can still use the factorization theorem in this setup. So here's that kind of situation in this exercise. So if we've got a random sample from the normal distribution with mean mu and variance sigma squared, we have two parameters, so like d is 2, and so this d is 2. And we're interested in checking whether if I compute the sample mean and the sample variance, so if I use x1 through xn and I compute the sample mean and the sample variance, and then I throw away the individual values, x1 through xn, have I lost any information about mu and sigma squared? That's what we want to check. And so we're going to check whether this pair of functions of the data is sufficient for this pair of parameters. Okay, so we can use the factorization theorem in this way. So to use the factorization theorem, we need to begin by writing down the joint PDF of the data. This depends on mu and sigma squared. And since I've got independent random variables all having the normal distribution, the joint PDF is the product of the marginal PDFs. So the PDF of the normal distribution with mean mu and variance sigma squared is going to look like this for each of the xi's. And so what I want to do now in order to use the factorization theorem is show that I can factorize this into the product of a function of x bar and s squared and a function of x bar and s squared and the parameters times just some function which does not contain the parameters. So let's see if we can manipulate this until I get something like x bar and s and squared appearing. So if I take this product, I'm going to write 1 over sigma raised to the power n. That's what I get when I apply the product to this 1 over sigma. Then 1 over root 2 pi raised to the 1 over n. And then it's like I have e to the minus x1 minus mu squared 2 sigma squared times all the way out to e to the minus xn xn minus mu squared over 2 sigma squared. So let's see what happens to this product. We know that if I have like e raised to the a times e raised to the b, it's e raised to the a plus b. So we're going to wind up getting a sum. So I've got 1 over sigma to the power n, 1 over root 2 pi to the power n, and then e raised to the, now I have the sum of the xi's minus mu squareds over 2 sigma squared. We're going to see this thing quite often from now on, that this product turns into a sum when I take it up into the exponent. Okay, so we need to get comfortable with that. And so now I still want to manipulate this until I get an x bar and an s squared coming out. So the way I'm going to do that, this stuff I can just copy paste down here, and then I've got all of this stuff. I'm going to write this sum by adding and subtracting x bar like this. And now let's see what I can do with this thing. I have the sum of xi minus x bar n squared. So expanding the square plus 2 times the sum. Well, let's leave the sum outside of it for now. So let's just expand the square. Okay, so I'm going to get this thing squared plus the cross product. So 2 times xi minus x bar times x bar minus mu. Make more space. Plus now this thing squared. So I get x bar minus mu. I like to keep these subscript n on my mean. Okay, so this sum is equal to this thing. Now I want to take this sum and distribute it to each piece. So I get, for the first piece, the sum of xi minus x bar squared plus 2 times the sum xi minus x bar times x bar minus mu plus, and when I take the sum of this one there's no index I in here, so I'm just adding this thing up n times. So I get n times that thing. Let's continue to simplify a little bit more. This thing I think we've seen before. This is always 0. Okay? If I take the sum of the deviations from the mean, I always get 0. Okay? That's because I know that the sample mean is 1 over n times the sum of the xi's. Okay. So that if I do, that means the sum of the xi's equals n times x bar. And so sum of the xi's minus nx bar equals 0. And that's like writing this, so it's got to be 0. Okay, so what I get in the end is that this thing is 0. This thing, let's go ahead and rewrite it. Remember my sample variance was like 1 over n minus 1 times the sum of the xi's minus x bar squared. So if I move the n minus 1 over to the other side, then I can say that n minus 1 times the sample variance is this sum. So I'm going to write this as n minus 1 times the sample variance plus n times x bar minus mu squared. And that was what all of this turned into. So let me come all the way down and write finally 1 over sigma to the power n, 1 over root 2 pi to the power n, e raised to the negative 1 over 2 sigma squared times n minus 1 Sn squared plus n x bar n minus mu squared. Okay, if I want to simplify it maybe a little bit more just to make it look different, I can write it as minus n minus 1 Sn squared over sigma squared. Okay, 1/2 times that minus 1/2 times n x bar n minus mu squared over sigma squared. Okay, what in the world were we trying to do? Again, this is, let's remind ourselves, the joint density. We can write its dependence on mu and sigma squared explicitly like that. That's just the joint density of the data. Okay. And what I wanted to show was that I could write it as some function of Sn squared x bar and the parameters times some function h of only the data and not the parameters. So what I can do is say this whole thing looks like my function of the sample variance and the sample mean and the parameters. And you know what? I can just multiply it by 1 and call this 1 my h. Why not? Okay. So, yes, by the factorization theorem, x bar Sn, this pair of statistics, is sufficient for this pair of parameters, mu and sigma squared. So if I have a random sample from a normal population and I want to know about mu and sigma squared, it is sufficient for me to compute the sample mean and the sample variance. these quantities tell me everything I can know from the sample about mu and sigma squared. And that's because we were able to write down the joint PDF of the data as a function of these two statistics and the parameters times some function of something which doesn't involve the parameters. Okay. Let's do another example. We can also use this factorization theorem to find a sufficient statistic for a set of parameters. So let's say we just have a situation like this, and I don't know if there's any way I can reduce the values x1 through xn to maybe one or two numbers without losing any information about the parameters alpha and beta. We can find such a reduction of the data for alpha and beta by using the factorization theorem. So I want to discover a sufficient statistic. So I'm not given in this exercise a statistic, but I want to discover a statistic that is sufficient. So what we're going to do is just write down the joint density of our data. We can emphasize its dependence on alpha and beta by dropping those in there after a semicolon. Since I've got independent random variables, this is the product of so many gamma densities. So xi alpha minus 1 e raised to the minus xi over beta. Let's make that prettier. And let me just go ahead and keep the indicator functions which tell me that the support is greater than 0. So in order to discover a sufficient statistic for alpha and beta, what I'm going to do is try to simplify this so that I get some kind of functions of the data appearing. And then I'm going to look for a function which involves those statistics and the parameters. And if I have something that looks like a factorization of the joint PDF into two functions as described in the factorization theorem, then I will have found sufficient statistics. So this product is going to look like 1 over gamma of alpha beta to the alpha x1 raised to the alpha minus 1. I'll do e raised to the minus x1 over beta times all the way out to xn to the alpha minus 1 e to the minus xn over beta. Let me drop in the indicator functions. This first one is going to be x1 greater than 0. The last one is going to be xn greater than 0. When I take this product, this thing is going to show up n times. So I'm going to get 1 over gamma of alpha beta to the alpha raised to the power n. I'm going to get the product of xi raised to the alpha minus 1. So that's this one. All of those are going to look like this product. And now these guys are going to be product of e to the minus xi over beta. And then all these indicator functions I can write in another product like this. Okay. So I don't exactly see sufficient statistics jumping out at me yet. Let's keep simplifying. So in front I've got this thing. Let's take a look at this. Each term in the product is raised to the power alpha minus 1. So I can write this as this whole thing to the power alpha minus 1. Now let's look at this guy. This is like e to the minus x x1 beta times e to the minus x2 beta all the way out to e to the minus xn beta. So if I add up all of these, I'm going to get e raised to the minus sum of the xi's divided by beta. And then over here I've got the product again of these indicator functions. All right. What I'm looking at now is, can I maybe break this up and call this h1 through h of x1 through xn? Because this is a function which involves the data values but not the parameters. And now this other function contains like these two things. So what if I call that one of my statistics and I call that the other statistic? So maybe my statistic has two pieces. The first one is the product of the xi's. The second one is the sum of the xi's. Then this whole thing is some function of the product of the xi's and the sum of the xi's and the two parameters. So if I were to propose this pair of statistics as a potential sufficient statistic and then go through the factorization theorem, I would be able to show that these statistics are sufficient for the parameters alpha and beta. So this tells us that this is a sufficient statistic for the pair of parameters alpha and beta. We'll end this lecture with a result which I'm not sure quite where it should fit in the lecture, so I'm just doing it at the end. There's a result which says if we have a random sample from any distribution, or we'll say any continuous distribution, okay, so this is like a PDF, then it doesn't matter what the parameter is. It could be multiple parameters inside of this theta, or just one. If I take the complete set of order statistics as my statistic, so remember this is like my x1, which is less than x2. That is, if I just sort the data, that is always a sufficient statistic for theta. It seems kind of silly. I mean, if I take my x1 through xn and I just sort them, obviously I'm not losing any information about any parameter because I'm keeping all the original information that was in the data. But this is a result that's kind of well known. And if you know it, you can say, well, we know the set of order statistics is sufficient for any parameter. And then you can, I don't know, sound smart. So to show it, we're going to go back to like the original way that we were showing sufficiency. And that is, we're going to take in the numerator the joint PDF of the random variables in the sample. And now in the bottom, we're going to take the PDF of the statistic. Okay, so our statistic is now consisting of n values. So let's call them like x1 through xn sorted. We'll emphasize some parameter on, we'll emphasize dependence on the parameter theta by putting it there. So I want to check whether theta cancels out of this. Okay. So here's how we'll do that. In the numerator, we've just got the joint PDF of all the random variables in the sample, and that is going to be the product of this density, this one, over all the x's. Okay, and in the denominator we've got this one. It turns out we can show that the joint PDF of all the order statistics is also given by the product of the marginal PDFs times each one, or the product of the marginal PDFs plugging in each of the order statistics. Now, up in the top, it doesn't matter in which order I take this product, so I don't change anything if I just go through that product in the same ordering that the data values have. So basically I get 1. Oops. So, so theta cancels out, which means the complete set of order statistics is a sufficient statistic for the parameter theta.
It's time for the flip.